Welcome to GemChem. Now today's video is on group chemistry part 4 video, and here we are going to deal with the particular question: carbon exhibits extensive catenation property, but this property is not generally shown by boron and nitrogen. And we will also see few trends about group 13 elements, that is p block elements. Now before starting, already 3 videos are uploaded in channel. You can watch it. I will give the link in the description box as well as the I button present above this video. And if you are new to GemChem, do not forget to subscribe the channel and hit the bell icon for regular updates. Now let us start. So first of all, why carbon exhibits this catenation? So if you remember, then in case of nitrogen, we can observe that nitrogen has a lone pair in it, right? When it bonds with another nitrogen, there is a probability of lone pair repulsion. So this bond is not much stable. Similarly, if we consider for oxygen, then there are 2 lone pairs, right? So 2 lone pairs, and again this oxygen has 2 lone pairs. So this is having again a lone pair repulsion. But in case of carbon, this bond is much stabler because there is no lone pair, as well as the small size is also the case. So we can say that if you consider, first of all, it is due to the small size of the carbon and absence of lone pair, the carbon-carbon bond dissociation energy is very high. As a result of this, the carbon-carbon bonds are very stable, and this favors catenation. Unlike the case of nitrogen, where we can see that due to the small size of nitrogen and due to the presence of lone pair, there will be an extensive lone pair repulsion, and thus catenation will not be favored. Similarly, for case of catenation in boron, if you see, then boron is not allowed. Why it is not allowed? If you see, boron has a deficiency of electron in it. So it is not allowed. As hypothetical catena, boron will be unstable due to the electron deficiency at each boron center. There is a vacancy in each boron center. So when they bond, these vacant orbitals creates a problem, right? So next we will deal with group 13 elements. Now for this particular video, we are going to deal with trend in elemental state, trend in oxidation state, Lewis acidity of halides, bond length of boron-fluorine bond in different compounds. Now before starting this portion, you have to understand that few topics from the periodic properties is required to understand this topic. So first, do see all the videos of periodic properties. I will give the link in the description box as well as the I button present above this video. Now we will see first trend in elemental state. So first boron. Now we know the elements to be as boron, aluminium, gallium, indium and thallium. So how does boron exist? Boron exists as B2. So if you see here, first case is that B can exist in the form of B2, where the 2 boron centers are held together by a pi bond formation, and the pi bonded electrons are of parallel spin, means the bond which is being formed is formed by a parallel spin electrons. Next is that aluminium does not exist in the form of Al2, because we know that the size of aluminium is large, and since its size is large, so it is not possible to form a p-pi bond, as a result of which it exists as monoatomic in nature. So it is monoatomic, right? Now next one is our third, that is gallium. Now gallium is placed as Ga2 and it is liquid at room temperature. So why it is liquid at room temperature? This is very important to understand. So first of all, this has a kind of bond which is known as intra-layer gallium-gallium bond. That is, the 2 layers of gallium-gallium bonds are being bonded together by a weak bond, and a strong interlayer, that is within the layer there is a gallium-gallium strong bond, as a result of which the former, which is the intralayer bonding, gets broken at room temperature, while the interlayer, within the layers, the bond remains stable. So it can be easily converted to gallium to liquid. Next is that the last one, which is indium and thallium, are monoatomic. So why is it monoatomic? Because it has a larger size and it cannot participate in pi bonding. Next comes trend in oxidation state. So in order to understand the trend in oxidation state, it is important to know the configurations, right? So these are the configurations. From here only we can understand that one of the electrons can get easily transferred, right, which is present in the p orbital. But this is not the only case. If we consider this is our ns and np orbitals. So here is the three places. Here is ns and here is np. So due to the low promotional energy of these electrons, one electron easily goes to this part in the vacant orbital. As a result, ultimately our configuration looks like this. So this is one and this is one. So what we can say is that there is a low promotional energy from ns to np. Thus there are three unpaired electrons, as we can see here in the outermost shell. So each of these, boron, aluminium, gallium, indium, all these exhibits monovalency. Boron, aluminium, gallium and indium can exhibit also trivalency. From this part we can understand that it can exhibit monovalency as well as trivalency. But the exceptional case is Tl, that is thallium. If you see this configuration very carefully, there is a presence of 6s2. And as we have seen in the previous videos of periodic properties, this is the inert pair. As a result of which there is an effect of inert pair effect. There is a relativistic contraction of this orbital. As a result of which this cannot easily give up the electron to the p orbital, and thus it exhibits stable monovalency. So what we can say is that there is a low promotional energy from ns to np, thus 3 unpaired electron and trivalency, and this thallium exhibits monovalency due to the relativistic contraction of 6s, leading to the inert pair effect, that there is only one outermost electron, hence thallium exhibits stable monovalency. Now if we further discuss on this stable monovalency, then we can say that suppose you consider this configuration. So this is our 6s and 6p. Right, here is the 2 electrons and here is 1. As we have already observed, no promotion is being allowed, and the configuration we also know. So first reason is inert pair effect and relativistic contraction of 6s. So we have to write down about the relativistic contraction of 6s along with the electronic configuration to be mentioned at the first, which leads to inert pair effect. This has to be arranged in correct manner. Another point is that if we consider for the second part, that is Tl3 plus 2 electron provides us Tl plus. In this case, the potential, that is reduction potential, is very high, positive. High positive. So what does it imply? It is due to the high positive standard reduction potential of this couple, that is thallium 3 plus and thallium plus, that the thallium 3 plus compounds are quickly reduced to thallium plus, the former behaving as strong oxidant. So this one is behaving as strong oxidant. Now remember, this is also a part of redox chemistry. Redox chemistry is also completed in channel. You can watch it. I will give the link in the description box as well as the I button present above this video. Now the next third point is that if we try to draw a Frost diagram, if we show this Frost diagram, see this very carefully. Here is 1, here is 2 and here is 3, and this axis shows n, that is number of electron transfer. then thallium comes here, and in the down portion comes thallium plus, and here is our, in the 3 portion, thallium 3 plus. So this is thallium plus and this is thallium. And if we try to join this, then this comes like this. So also from the Frost diagram of thallium, it is evident that thallium plus is most stable as it lies the most lower in the energy and is most stable. Since thallium plus lies below the line joining thallium and thallium plus, the latter two will come proportionate, that is to form the former. That is, if we have thallium, it will form thallium plus. If we have thallium 3 plus, it will also form thallium. Right. Now we will see the next property, that is order of Lewis acidity of BF3, BCl3, BBr3 and Bi3. Now first we have to know the bonding in BF3 in order to understand this better. So for BF3 we have F, B, F, F, right? And for the boron we have the configuration like this. This is 2s and here we have 2p, right, which is in the ground state. So here comes the electrons. Low promotional energy results in the transfer of electron to this part. So we can write it as equal to this with 3 electrons here, right? And this will be hybridized as sp2 hybridization. What we get is somewhat a delocalized p-pi back bonding. Here fluorine, boron and the 2 fluorines on the both sides, and if you draw the orbitals, this is an orbital with 1 electron, right, as we can see, and these orbitals are filled up, which are present here, 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 another here, another here, and these are filled up orbitals. If we consider, these are also having 1 electrons. This is 1, this is 1 and this is 1. These electrons actually undergoes a bonding within them. There is a bonding which is known as delocalized p-pi back bonding, which is important, right? So this p-pi back bonding along with the normal bonding is present. This direction is like this. It is coming towards the boron. So if you can see this bonding, so from here we can conclude that greater the size of halogen, longer will be the Bx distance and weaker will be the extent of back bonding, because as these sizes increase, it will be farther apart and the bonding will have weakness in it, and hence the electron deficiency in boron center will be higher, accounting for Lewis acidity. So if these atoms go away, then due to back bonding the compensation will decrease, and if the compensation decrease, the boron will become more and more Lewis acid, as a result of which the format of this order of acidity is BF3, then BCl3, then BBr3 and at last Bi3, right? Now we will see the next and the last question of this video, that is we have to compare the BF lengths in BF3 and BF4 minus or Me3N BF3. Now we have already seen the structure of BF3. Now we need to see the structure of Me3N BF3 or BF4 minus. Now in BF3 we have already seen that there is a extensive back bonding, and this back bonding leads to a double bond character. Extensive back bonding leading to a double bond character. And if you see here, then BF4 minus looks like a tetrahedral structure with a negative sign. This is the negative. And Me3 BF3 looks like this. N has a positive charge in it. Me, and Me, and here in the down portion BF with the negative charge, F, and F. Now Here we have single bond character and we have sp3 hybrid orbital sticking part. So first of all, we can say in BF3 there is an extensive delocalized p pi back bonding, and since the boron is electron deficient, such back bonding in BF4 minus and Me3 NBF3 is not possible. And since the boron contains the negative charge, hence the above two species, the length, bond length which we are searching for corresponds to the bond length of fluorine and boron or single bonds. Whereas in case of BF3, it is of double bonds. Hence, these bonds in BF4 minus and this compound Me3 NBF3 is much longer than in case of BF3. And secondly, we can say that in BF3, hybrid orbital of boron that participates in the bond formation in this case is actually sp2, right? This is sp2, while in case of this it is sp3. So, greater the s character of hybrid orbital, which is in this case greater s character. So, as a result of this, we have already seen if there is greater s character, the bond length gets decreased. So, shorter will be the BF length. Thus, BF length in BF3 is shorter. So, we can conclude that this is shorter. BF3 has a shorter bond length than Me3 in BF3 or BF4 minus. So, this much for today. Hope this was helpful. Thank you for watching. Please do not forget to like, share, subscribe and comment.